I will now introduce you to my research. The title is Autonomy through Real-Time Learning and OpenNARS for Applications. And the outline is as follows. At first, I will talk about the research question itself, about increasing system autonomy via a real-time learning approach. With architecture, we will see. And then we will dive into the non-axiomatic reasoning system foundation, which I have used in order to create this architecture, ONA. And then we will dive into comparisons with existing techniques, including reinforcement learning. There we will see comparisons on simulated examples, also comparisons with BDI model, belief, desire, intention models, with a robotic example included. Then I will show, then I will simply list again how the research question was answered. And then I will talk about future plans as well. So let's start. Why real-time learning? Real-time learning gives species in nature clearly key advantages over others. So they can change their behavior and adapt to changing circumstances, and then use this to exploit the environment for their own purposes. So this is a good feature. Also, it can be seen as also part of the difference between general purpose intelligent systems and more special purpose solutions. And additionally, when we look at current AI systems, often real-time learning is not necessary. Often it's possible to pre-program and to train them before deployment. And but for the autonomy I have in mind, adaptation at runtime is crucial. And so we will focus also on this real-time learning aspect, which brings us also to the research question, which is whether a non-axiomatic reasoning system implementation with its ability to learn in real time can enhance the autonomy of intelligent agents beyond what currently is available. And the reason, how to say, I have chosen a reasoning system essentially to get this done. And so the objective is to create an implementation of this non-axiomatic reasoning system or implementation design, which is especially suitable to be used for autonomous agents, and also to implement it in a portable and high performance manner so that it can be used for practical purposes. And then also to evaluate to what degree it can improve the functioning and autonomy compared to the existing techniques in experiments where adaptation at runtime is necessary. And we will see a few examples of this. But let's now go into the theory first, because this is where I essentially started. I started by using a non-axiomatic reasoning system, which was proposed by Dr. Wang. It's a general purpose reasoning system which operates under the assumption of insufficient knowledge and resources, which means that the processing demands are always finite. So it cannot happen that it starts some process which runs out of memory or something like that. It cannot happen because it's a constraint, memory constraint, and also constraint in how long an inference step takes. And it's open to new information at runtime, which is quite unusual for reasoning systems, because often you give them information and then you can start them and let them reason on to answer a query or something. But in NAS, it's a bit different, because while it's reasoning, new information can enter the system and needs to be addressed by the system. And also the operation of the system is in real time. So it has to react to new information as soon as possible so that it can meet potential time constraints. And the way this reasoning system operates is it's using a logic like most reasoning systems, and in this case in particular a term logic which is able to deal with uncertainty. And we now see this term logic. There can be it's centered around terms which can either be atomic, such as a cat, an animal, or compositions thereof. And so that is a bit different than existing model theoretic approaches, because the meaning of these terms is not defined beforehand. The meaning of them is merely fluid and determined by the relationships these atomics appear in, or these terms or terms in general appear in. And here we see, for instance, a few examples which how you can express more complex relationships with terms. For instance, we have this notion of a statement which is essentially composed of terms and copulas, and one copula, for instance, is inheritance, which is a special case, general case relationship, like a cat is a special case of an animal. Or here with curly braces, we indicate instances. The instance Garfield is a special case of an animal. Also, we can express statements like cat has property meowing, and this is how we would represent this. And additionally, there can also be temporal relationships, for instance, and or implications in general. For instance, that lightning leads to thunder would be expressed this way. In this case, often the atomics which are related with implication themselves statements, so it can be nested. For instance, we can say if the switch has property on, then it will also happen that light will have property on. And this kind of temporal relationships we will talk a lot about, because they are very essential to this real-time learning ability. And especially decision making, as we will see. But before we go into there, let's look into the truth value. In many reasoning systems, truth value has positive. Truth value is either true or false. But in NAS, it's a bit different. Non-axiomatic logic uses two real values to indicate the truth of a statement, which is a positive evidence value and a negative evidence value. So positive evidence is what supports a statement, and negative evidence is what's against it. But we will see this in more detail very soon with examples. And based on this two evidence values, frequency value can be defined, which is the positive evidence over the total evidence, so the positive plus the negative, and also a confidence value, which is the total evidence over total evidence plus 1. So it maps the total evidence into an interval between 0 and 1, never approaching 1. And why do we need these two values here? If we look at this frequency value, it looks a bit like probability, right? Positive cases over total cases. But we do not take the limit here, which is a key difference, because we have not seen infinite amount of evidence. So we don't take the limit here, it's only the ratio. So the empirical frequency. And why we need this confidence value in addition is exactly to keep track of how many instances did we see. So NAS can essentially distinguish, for instance, is the coin fair? We could ask if we have 10 coin flips and 5 heads, then it would give less confidence than 100 coin flips and 50 heads. But in both cases, the frequency would be 0.5, because if we take this over this, it will or 5 over 10 and 50 over 100, it's both 0.5. So it can distinguish, so it can know how many samples has it seen about a certain relationship. In addition to the empirical frequency, success frequency for implications, we can also interpret it this way, but we will see this right now. So, for instance, if we want to be able to learn temporal relationships, they are really essential for the real-time learner. so that it can, but we will see this. So let's say we simply have a sequence of events ABC, and according to what we have seen with positive evidence, in this case, we have positive evidence for A leads to B. So we already see this implication relationship here. And also positive evidence for A and B together leads to C, and also positive evidence for A leads to C. So if we have this event sequence, this gives positive evidence to all three hypotheses. But what happens if A happens, but B does not? So we have an A, but we do not get B in succession, even though the implication relation would predict it. We would predict B to happen, but it does not happen, even though A happened. So what happens now is negative evidence is attributed to this hypothesis. So we can also say in this case that the frequency value of the truth value is the success of a temporal implication to predict the outcome. And we can also say that the confidence can be seen like how many examples of this have we seen, either of the positive or of the negative case in total. So we have both the success frequency and also how many samples have we seen is both encoded. And now we will finally dive into the architecture I have created, which is pardon. Oh, I think it's just background noise. OpenNARS for applications is the architecture. It's a general purpose reasoning system which utilizes the non-axiomatic logic we just have seen. And it's a pragmatic design which follows the NAS theory, which only combines the aspects which are quite proven and which with a focus on agency to be used in autonomous agents. And also there's a high performance multi-threaded implementation in C available. And the capabilities the system should have is to learn from event streams in real time and to do so without interruption. So it's really real-time learning we are after here. It should continue to learn. There's no separation between learning and test phase. The learning continues with every example you present the system, with every event which enters into the system. And from these event streams, it should be able to extract sensory motor contingencies, because what this is, let's say some events encode operations the system can execute. So it can, for instance, see when a certain operation event happens, and there were certain other events happening before, and then it also sees what's happening after. So it can form a relationship. Under this context, when these events are happening, and they execute this or that operation, then I can expect this different outcome events to happen. And when it's able to extract these sensory motor contingencies, it can use them to plan ahead to reach goals. And this is a key aspect of the system. And this is also central to enhancing autonomy, because clearly if it's able to learn new procedural knowledge, essentially, or such sensory motor contingencies at runtime effectively, this is clearly something desirable for autonomous system and can learn new knowledge on the fly. The architecture, the reason architecture looks like this. We will now go through the individual steps, how this works. But first we see, let's just dive into it. So we will simply go from left to right here, from the left side to the right side, and these are the major components of this architecture. And if we start from the left side, we see here sensory channels. These are responsible for taking in physical signals, can be different modalities, can be microphone, can be camera, can be different ways to take in information via sensors. And then to pre-process this information, and this can happen in very modality-specific way. For instance, we can have different processing for visual processing, for instance, we can use a machine learning approach there, like the convolution in neural nets, like we will also see, and take this output of the neural net, for instance, which can be a label, and also the bounding box, which also gives us location information, and encode this into events and statements we have seen, statements of the form we have seen, and this then goes into the FIFO sequencer, and this sequencer does nothing else than to take in the different events generated from the different sensory channels and put them into the sequence they appeared in. So if we got an event A from the visual sensor and event B from microphone, for instance, and B happened after A, then we will have a sequence AB in this FIFO sequencer. So it simply creates the sequences of the information in the order it entered the system, and from there it goes into the attention buffer. And this attention buffer ranks items according to a priority value, which we will see which also depends on the truth value and the evidence which is attributed to a certain event. So if a statement has a lot of evidence, it will also tend to have a higher priority here. This is a key aspect here. But both of these data or the data structures are bounded. And so there needs to be some kind of eviction strategy to keep them in bounds. And for the FIFO sequencer, it's straightforward, because for this data structure, it's simply an array, first in, first out array, where all the items are removed first. And for the cycling events queue, or attention buffer, as often simply called, it's a heap data structure, which and in this case, the lowest priority item is removed in order to make place for new items. So these are both bounded data structures with two different eviction strategies. And here is concept memory. This one is a bit more complex. This one is essentially it's storing the beliefs the system has formed from experience, so the patterns it has learned from event streams essentially, and so it stores all the evidence of the relationships, like lightning leads to thunder. And for instance, if we get some lightning event in here, it will, and it selects it from the attention buffer, it can now select this lightning leads to thunder relationship from concept memory, which stores the relationships and the evidences. So it can now use lightning and lightning leads to thunder to predict thunder. And this prediction is done by a sensory motor inference, in this case, because it's a temporal relationship, because in this architecture, it distinguishes between semantic relationship, which is essentially a common term between both premises, and also a temporal relationship, or temporal relationships like implication relation is processed in sensory motor inference, and semantic relationship on the top. But we will now see examples of these inferences. And the results go back into the attention buffer to compete for attention. And so it's whatever will have high priority will be processed and lead to further derivations, either through semantic or sensory motor inference. And for semantic inference, the way this looks like, I already mentioned, there needs to be a common term between the selected event and the belief. For instance, let's just look at one example. If S is a special case of M and M is a special case of P, then S is a special case of P by deduction. So if Garfield is a cat and the cat is an animal, then we can derive that Garfield is an animal by deduction. In this case, M is the common term between both premises, and this is semantic inference. For sensory motor inference, there's always, as I said, temporal relationship between the premises. So for instance, if we get events A and B, we can create positive evidence for the implication. So we have A and B happened after A. So we can create this implication relation to add a bit more evidence to this relationship. And also we can use it for prediction, as I already mentioned. If we have an A and we also know that A leads to B in concept memory, then we can predict B. Sensory motor inference is also responsible for processing cores, which is really central to this architecture, since it's also supposed to be able to do decision making. And so in this case, a central capability is subgoring. If you already have a goal G, and you have a way to achieve G, like if in context C, if I execute operation up, then I will get G. So if the context is fulfilled, so we have the C, and we also want G to happen, then what we need to do is to execute the operation, right? But it's not as simple because often there are multiple candidates how we can get G. There are multiple implications which say under this and that circumstance, even in same circumstances, different operations can lead to G with different proof value. And here it's a key to select the operation which most likely leads to G to happen in the current circumstances. So it really makes a choice here and really derives the operation to execute the operation with the highest, where the implication has a very high proof value, and also the context event has a high proof value. So it always tries to select the option which most likely leads G to happen. But sometimes there is no way to go from current context to the core with a single operation. Sometimes you need to do multiple action steps in order to get from a current context to a core. So when there is no such operation which is above some truth threshold, desired threshold, what it will do is it will derive the context events, the contexts like C in this case, as a subcore. So this is central. There's also algorithmic form, but I already explained it here essentially. So it's really decision making where the actions it invokes should be the ones which most likely leads to the fulfillment of the goal under current circumstances, but sometimes there is no single step possible, so you need to achieve the previous step first. You need to achieve the context, which then can potentially lead to G with some operation. So sometimes you need to do the sub-calling, and sometimes it doesn't work to do a single decision step. Overall, the system, the usage should be quite straightforward. It's like black box is maybe not the right word, because you can investigate what's in concept memory and so on. But from usage perspective, there are three types of events which can enter the system, which is either belief events. So these are just like a sensory state. Currently, temperature is above 20 degrees Celsius, or can also be a goal. I want the temperature to be above 20 degrees Celsius, or a question, is the temperature above 20 degrees Celsius? And the way this is encoded, there's some term like temperature inherits some value, question mark would be a question, for instance. But if it's a belief, there's a truth value attached, some default, usually some default value for inputs. So often you only need to decide on what to encode, what term to use here. And the output of the system is either operations the system wants to execute to achieve some goal, or the answer to a question. So this is how the system can be used. So this is quite straightforward. And now we will see some comparisons. I did in Parallelium 2, I talked about more different approaches, but here I will focus essentially on mostly on these which I have compared with in practical experiments. And one, for instance, is a particular reinforcement learning technique, Q-learning, with table-based implementation. What's quite good about Q-learning is clearly it's able to solve the temporal credit assignment problem for behavior learning. So often, especially if you need to achieve a certain outcome, often you need to do multiple steps from current circumstances, as I mentioned, to get there. And how much is a past action you took responsible for that you really reached the outcome you wanted? And so this is a difficult problem. This is the temporal credit assignment problem. And this is quite nicely solved by Q-learning, which is formalized like this. But it's only doing so for one outcome, which is a reward signal. So all the representations it learns are essentially what action should I take in a given state, namely the action with the highest expected utility. This is what Q-learning essentially does. So it always tries to take the action which essentially tries to maximize the reward it will get. But what if we are not only interested in learning such relation, not only interested in what should I do in a certain context, but also if I want to know what is the consequence besides reward of invoking a certain action in a given circumstance, then this is already out of this technique. But I'm getting a bit off track here. A key here, before we go into this comparison with the representation it learns, it's also important to mention before. For instance, there is a learning rate alpha in this equation here, which is often manually decayed over time. And this is also a weakness of Q-learning, because it means for a given example, you need to choose a good learning rate parameter. If you don't choose a good one, it might not converge. You might not get a good learning performance, and so it's very dependent, and also dependent on this learning rate, and especially also its decay. And in NAS, there is no learning rate decay as such. There's simply this fact that knowledge becomes more stable if it has more confidence. If the confidence of a truth value is higher, then the related belief, the frequency of the related belief will not change much by a single new observation. So in NAS, it's essentially the confidence value which stabilizes knowledge. There's no need for assuming that the passing of time itself can be equated with gaining more experience about certain relationship. What I did then was to compare, do some comparison. For instance, in Space Invaders, quite a straightforward example. There is some kind of alien which needs to be shot by the spaceship, and the spaceship can move to the left or to the right and can shoot. In this case, it can observe when the alien is on the left side or on the right side, or if it's aligned, and gets essentially a reward when the alien is shot. In NAS, this is encoded via goal fulfillment. So in NAS, essentially, the reward is encoded as a goal. The system wants satisfies. So there's for NAS there is alien shot additionally, which stands for reward essentially. Because when comparing both techniques, I had to make sure that both receive the same states, but to make up for the additional reward state, in NAS I use alien shot state for OpenNAS for applications. What I found in this particular example is that the learning performance of the Q learner was more inconsistent, but sometimes, how to say, sometimes it was very fast, sometimes it was slower than ONA. But in ONA, the learning performance was more consistent in this particular example. But the performance overall, as you can see, is quite comparable in both systems. We will also see a summary table of this. But in this case, there is not a too large difference, except that in this case, this ONA's performance can be said to be more stable in this particular example when it comes to different starting positions and random seeds. Yes, and for the Q learner, I was using epsilon greedy so sometimes it executes a random operation. so that it can essentially try something it has not yet tried, so that it can learn something new. And also in owner, I use a random action selection. Then from them, so there's a certain random parameter where it rolls a dice, and if it's above a certain value, then a random action will be taken instead of the best known one for the case. Just additional detail. Also, additional example I tried was grid robot. Here the task is to collect food on a grid. There are also obstacles around. The robot needs to navigate around, and it only sees what's on the left, forward, or on the right, and for a certain range, like 10 grid cells of distance, and always sees the nearest object. And the states in this case are a combination of foot left, foot right, foot front, or there can be a war on the left, or on the right, or on the front. And reward is given in this case when driving over a foot object. But this is the only feedback, which is quite delayed reward. There's only rarely reward events happening, because it only happens when it really drives over this foot, such a foot object. In this case, of course, how to say, Q-learning is good also for delayed rewards, because also use this eligibility traces extension, and also owner performed, in this case, they performed comparably. Owner was a little bit better, but this is an artifact of randomness in this case, because it was 10 trials for each method, so we can only say it's comparable in this case. Additional, then I tried another example which gave me a more surprising result finally. I had a Pong game which has 3 actions, left, right, and stop. And again, it's in this case, it sees when the board is left and the board is right and when the board is aligned. And the interesting thing here is, for some reason, I didn't get good performance with the Q-learner. And at first I was wondering why. And then it became clear. The way these actions are coded, left and right, are such that the right and left movement is only stopped if the stop operator is called. This means that these actions have consequences beyond that they still act on the next frame, so to speak. And this is already non-Markovian. Reinforcement learning, many approaches, especially Q-learning, assumes Markovian environments. So essentially, the next state and reward only depends on the previous state and previous action taken. But with this action encoding, this is not the case, because the left operation causes the agent to continue going to the left or continue going to the right. So even though it's a quite simple environment, this Q-learner had an issue here because it assumes Markov property of the environment, which was violated in this case. But for owner, this was no problem, because it does not make the Markov property assumption in the first place. And then to investigate, to see if this was really the issue, because of course when implementing software there can be other bugs as well. So also then I changed this operations to only move to the left or to the right as a particular step says. So it does not need to invoke the stop operation in order to stop the movement. And then it's both performed equally. So it was really this violation of the Markov property which caused the Q-learner to struggle in this particular example. And yes, and overall I can say that there is comparable performance of both techniques. So owner is a viable alternative for reinforcement learning, except when environment is non-Markovian, then at least for the Q-learning approach, this one struggles with it. And we see this also reflected here in this table, Space Invaders, and we get similar numbers, but in the non-Markovian Wang, owner was with 0.8 right above the 0.61 success rate of the Q-learner, which did not improve further. And also in simplified Wang, it was again comparable, and also in grid robot, comparable performance. Additionally, it was quite convenient actually with the Q-learner to get similar learning speeds. I also needed to tweak the learning rate a lot, which I did not need to do for owner. So this was quite good, which is also good for autonomy if you don't need to tweak the learning parameters. If the designer does not need to do so, but it can itself learn successfully even without tweaking hyperparameters too much. So in this case, owner has a bit of a benefit. Yes, and also this is of course because of the property I mentioned, that the beliefs of the system or the statements and the truth value become more stable automatically with the accumulation of more evidence. So it does not need such a decay parameter choice. Additionally, also the exploration rate decay, I did not really need to decay it in owner because I have a mechanism inbuilt when the hypothesis is having how to say, if it has if it's predicts successfully, let's put it this way, then it does not use model bubbling in this case. So it does not try random actions anymore. So it's like it by itself reduces its exploration rate by the evidence accumulated for the procedural knowledge, which is good if you don't want to tweak hyperparameters much to get good learning performance or learning speed mostly. The second paradigm I compared with is belief, desire, intention models. They are the main paradigm, or a main paradigm, I should have said, maybe for autonomous robots. It consists of beliefs which encode current facts the agent knows, and desires which are forced to select to plan for, and also intentions which are the desired pursuit, which are actually desires which are pursued as goals. So the system actively tries to achieve them by the selection of viable plans. A key difference is these systems are often used because it's easy to encode background knowledge, human background knowledge, because it's essentially mostly predicate logic or first order predicate logic representations they use in these models. And which is good for if you have background knowledge and you want the system to use it for planning and so on. But it's not good if the system should learn knowledge on the fly, because it does not support this. But NARS can clearly do this with the learning of these temporal relationships. So, and we can also see NARS as a PDA model which learns our extension. Yes, which it can also achieve multiple objectives, so there can be multiple goals, but this is also the case for PDA models. But a key thing here is clearly that a behavior suitable for one goal is often not suitable for another. So it's this is already in the reinforcement learning less straightforward to encode. For instance, a goal can be encoded as part of the state. But then again, the knowledge the reinforcement learner learns will not generalize to other goals well, because different states means different procedure knowledge, different Q table entries, I mean, which need to be maintained. Yes, and especially if learning at random is concerned, then learning speed is a crucial metric which should not be ignored, because especially if you go to robotics application, you cannot use large-scale trial and error. And yes, and of course, it would be good if roboticists would have a tool where they can both easily integrate background knowledge and where behavior learning is nevertheless possible as well. Yes, and owner addresses these concerns. And an example I did was with a Lego robot, which with following hardware, it has two motors for driving, one gripper, and an ultrasonic sensor for distance reading to obstacles, and additionally a smartphone which I mounted here on the backside of the robot, which provides vision to the system. For software-wise, I have created a little vision channel based on a machine learning model called YOLO version 4. Actually, I moved to there's also a tiny version which can directly run on the smartphone, which is quite convenient. And I used the darknet C implementation in particular. So this was used for visual object detection. And ONA was used for the real-time reasoning, learning, and decision-making component of this experiment. And the key experiment I tried here, besides learning obstacle avoidance, which also can easily be done with a reinforcement learner, but what I also did is a more complex mission where it has to find and retrieve a bottle and retrieve it to a group of other bottles. So there's some bottle in the room, and it has to find it and grab it, and then it has to find the other group of bottles where it has to retrieve it to. In this case, what's special compared to PDI model is it's learning part of the knowledge. It's learning obstacle avoidance on the fly. And also it learns how to bring objects to the center so that it can lift them up. It learns both of this with this temporal inference, or with its ability to learn temporal patterns we have seen earlier. Additionally, like PDI models, some mission knowledge was given, namely how to really pick it up with some motor procedure, and also to drop the bottle to the other bottles when they become visible. So there's some mission-related background knowledge, which is often the case in PDI, but with the addition that some knowledge is learned at runtime. And compared to the reinforcement learning, of course, it's convenient that you can give mission-specific background knowledge. Then event encodings in this case were things like if there's the output of the convolutional neural net of the YOLO model, I directly use the label, and then I looked at the bounding box coordinates in order to create events like this. Could be, for instance, like cat is something which is on the left or on the right or centered. So it knows what was detected, and also how is it spatially related. Also, it knows of the gripper state, closed and open. So whether its gripper is open or closed, and whether there's an obstacle in front, whether it has moved forward or not, and also some mission goal, so that it is motivated to essentially find the bottle and bring it back. And the operations, moving to the left, to the right, forward, pick, and drop. And the hypothesis it learns are actually quite many already. It learns if there is no obstacle in front, then forward movement indeed leads to the robot to move forward. It also learns that if there's an obstacle in front and it it rotates to the left, the distance value will increase, or the obstacle observed event will not happen anymore. So it already knows how to do obstacle avoidance. So this is directly learned, and these are the representations it learns. And also, as I mentioned, it's able to learn to focus on arbitrary objects, so actually, because it can generalize, it can introduce variables for specific terms. Like if it sees a bottle on the left and it uses the left operation, and then the bottle will be on the center, it will also learn this more general relationship. This I did not talk about. This is too much detail for today, but it's in principle it can substitute a variable for a specific term in order to learn a general relation, which then also applies to other objects. So if there is a laptop on the left and it's moving or it's rotating to the left, then it will also be in the center, for instance. So it's quite essentially sensory motor contingency, which is learned from observation, from interaction with the environment. And the mission-specific background knowledge is only minimal, which is really only if there is a bottle in front and the gripper is open, then pick it. And if there are other bottles seen, and the grip is closed, then drop it in order to progress the mission. And from both this learned relationship and the minimal mission-specific background knowledge, it's able to accomplish this task quite reliable. At least in this case, again, the 10 example runs where it avoids obstacles with left movement, and it did retrieve the bottle in 10 runs successfully in this particular setup. Of course, in the future, I want to try more complex experiments with this, but so far it already proves that it's possible to combine learning and utilization of background knowledge effectively. Last, maybe I will only talk very briefly, because this is among the last slides now, about trusted and explainable artificial intelligence for saving lives. This is something we did together with chat proportion laboratory NASA. And here in this case, the system is mostly used for real-time reasoning about the situation. It should essentially assist and warn first responders on the mission. It should warn for potential collisions and also potential other risky situations. And the way we tested it was in the car driving simulator. And again, we took a similar approach. We took a YOLO version 4 as a detection approach, which was then combined with a tracker, which essentially tracks bounding boxes over multiple frames, assigns a consistent instance ID across multiple frames. And this information is then fed into the reasoner, and together with the background knowledge, it's then able to give, for instance, warnings. For instance, if there's a car approaching from the right side, or different anomalies which could potentially be risk relevant. And in this case, in event encoding stacking, just to list a few, almost finished. For instance, if there's a property, if some class and with a certain if a certain object, meaning it has a certain class ID from the YOLO, it can be a car. For instance, car number 2 can be approaching or leaving, and it also knows which direction. Is it on the left or is it on the right? It also knows how the speed of the objects, and also it has some lane detection with OpenCV, so it can also detect if an entity is driving within the lane or driving over the lane. So this all can be used to detect different anomalies. Yes, we don't need to go into the details here, but essentially there's also some background knowledge again, which, for instance, can say if there's a entity approaching from the left side with a high speed, then generate a warning, for instance, can be an example of background knowledge. Yes, and in conclusion, we can say there are some key aspects, because clearly autonomy is a broad term. There are many ways you can improve it. And this is also why it was important for me to find existing techniques and to compare with them on particular examples. And if we summarize some key points which enhance autonomy, for instance, is less dependence on learning rate decay choices, for instance, over reinforcement learning. Also, of course, this ability to easily express background knowledge. And also that the knowledge is inherently core independent, because it really learns different implications. If this is the case and I do this, what will happen next, which is not really dependent on which core is currently active or what is currently rewarded or not rewarded. So it's the most similar thing in the reinforcement learning literature is if you have a changing utility function, which in standard Q learning is assumed to be fixed. Compared to the PDI model, of course, the key benefit is this ability to learn knowledge at runtime, and I have then demonstrated with this practical applications the trusted explainable AI with chat proportion laboratory still in progress work, and of course the robot experiment we have seen that the system can be used to combine some of the benefits of what was else done in separation with reinforcement learning and PDI model and planning approaches. future plans, of course, will also, I want to move, I really want to continue research on autonomy. I want agents which can explore their environment via exploration and play, which can physically manipulate and utilize objects. The bottle collect mission was maybe a first example of this. And the system should, of course, learn from observations and interaction. It should ideally, it should be it should be able to remember places, objects, other agents, their property and behavior, which is a case of modeling of the environment, so to speak. And it should be able to do so as independent from a human as possible. Independence is clearly a part of autonomy. And ideally, if there are humans involved, it would be good if it could extract useful information out of human speech. But this is something I did not do much work yet on. But in the future, this is something I might also try again. I want to move more into maybe. Thank you for listening.